If Sangha, just wait, ma'am will join. Ma'am has already joined. Again, she will join.
Okay, sir.
After ma'am will join, I will ask you to introduce, then we'll start.
Okay, sir.
We'll start soon, no? Okay, let resource person join, then we can start. Just a minute. Priyanjana, good afternoon.
Good afternoon, sir.
So ma'am has already joined, so we just stop that previous meeting. So after ma'am will join, we can start.
Yeah.
Ma'am, good afternoon.
Yeah, good afternoon. Can you hear me?
Yes, ma'am. So Dipsankar, you just introduce to ma'am, then you can start.
Okay, sir.
Yeah.
So good afternoon, everyone.
Yeah, ma'am, any trouble in Zoom, then you just inform us so that we can.
So, Master.
Yes, Dipsankar, you can start.
Okay, sir. So good afternoon, everyone. Welcome to the second session of the day 2 of Summer School 2024. The session's topic would be speech signal analysis using PRAAT, and it will be taken by Dr. Sanghamitra Nath. It's my pleasure to introduce Dr. Sanghamitra Nath, an esteemed assistant professor from Department of Computer Science and Engineering at Tezpur University. Dr. Nath is a specialist in speech processing, natural language processing, embedded system, and microprocessors. She has made significant contribution to our field with numerous research publications and conference proceedings to her name. Her dedication to teaching and research is truly inspiring. Today, she will share her valuable insights with us. Please join me in welcoming Dr. Sanghamitra Nath. Thank you.
Thank you, Dipsankar. Ma'am, now your session is yours. Thank you, ma'am.
Yeah. Thank you, Dr. Dash. Thank you, Dipsankar. Dipsankar, right?
Yes,
Yes.
ma'am. Thank you, ma'am.
Yeah. Thank you, Dipsankar, for the kind introduction. So I'm audible, right?
Yes, ma'am.
Oh, okay. So I think I can start the session now.
Yes, ma'am. You can.
I'll
Session is-
share my screen. I'll share my screen. Please let me know if the screen is visible or not.
Yes, yes, ma'am. Yes, ma'am. It's coming.
Coming, right?
Yes, yes. Your slides are not visible, ma'am. The Zoom link something is showing.
Now,
No, ma'am. Ma'am, so your screen is there.
Yeah.
You have shared the screen, but that slide is not visible. Your slides. I think we have to select that particular slide. You just stop sharing again.
stop.
Stop sharing. Yeah. Again, just share the slide. Then only multiple screens you have to select.
I think now it is visible.
Yes, yes, ma'am. It's visible. Make it full screen. Yeah. Yes, yes, ma'am.
Okay, a very good afternoon to all of you. So, as I have been informed, I think many of you or most of you are do not have a background in speech processing, right? Am I right?
Yes, ma'am.
Okay. So, I'll go very slow. The very basics of speech signal analysis, and we'll be talking about the speech signal, the speech production mechanism, then how speech is communicated, then speech features, and then we'll move on to the different types of analysis that can be carried out on the speech signal, right? And that will be followed by hands-on using the PRAAT tool for phonetic analysis. So this is a tool which is very popular with researchers in speech phonetics. So I'll be using PRAAT to carry out the speech, all the analysis that is required for the speech signal, okay? So I've already shared a few the audio files. I think that has been shared by Dr. Dash. So you can, when I tell you, you can open them. I'll show how to open. I had also shared a link from where you can download the PRAAT tool. So I hope you have that. And if you have not yet installed, then you can install the PRAAT tool. It's very simple. You simply have to download the exe file and then run it, and your system will be there. It's very simple. Okay. So I think that you are already ready with the PRAAT tool, and we'll do a small hands-on session, the basics of speech processing using the PRAAT tool. Okay. So let me move on to the contents of this presentation. So on one hand, I'll be talking about the speech signal and the speech production process, how speech is communicated, the information that the speech signal carries, then the features of the speech signal, various speech tasks for man-machine interface, and then some common analysis like pitch analysis, intensity analysis, spectrographic analysis, and format analysis. Okay. And on the other hand, I'll be introducing you to the PRAAT tool, where you will learn how to create a speech object, how to do a preliminary processing of the speech signal. I'll show you how to filter the speech signal maybe. And then we'll see how we can annotate the speech waveform. And we'll do some basic analysis that I mentioned now, like pitch and intensity, then spectrographic format analysis, and so on. I'll also show you how to read spectrograms and just introduce you to PRAAT scripts. So now, let me first tell you what exactly is the speech signal. So all of you are already familiar with speech. You know what speech is. You know what is a speech signal, because we have been talking since the age of say 2 or 3, and we have been producing different speech sounds, right? So the sounds, I would say sound and speech is not exactly the same. Meaningful sounds, when you combine sounds to give meaning, then you make a speech signal. Okay, so I can say that speech signals are sound signals which are defined as pressure variations traveling through the medium which is the air. So whenever I want to say something or produce some speech sounds, I will be producing it, and the production will be starting from my lungs, where I will form the pressure and then air pressure, and that pressure I will blow from my mouth to produce the speech sounds. So these pressure variations will travel through the air, and then it will reach the listener, the ear of the listener, and then the listener will hear whatever I'm saying, just like now I'm doing. So you are listening to the speech signals that I'm sending you. Now, before I can process the speech signal now, I have sensors, for example, like the microphones, and these microphones, what they will do is that they will convert the air pressure variations into electrical signals like voltage signals or current signals, and these signals will be used in speech processing. Before these electric signals can be processed by the computer, we need to do another thing, and that is the analog to digital conversion. So you have ADCs which will convert these analog signals. The speech is an analog signal. So this analog signal will be converted to a digital signal, and then the digital signal will be stored in the computer. So a speech signal is represented by a sequence of numbers which represents the relative air pressure at various instants of time, say n, where n is a natural number. So these are the samples of the speech signal. And here I'm introducing a new term, that is the sampling frequency or the sampling rate. That is the rate at which you sample the speech signal to get the sample. That means at instance of time, you take a sample of the speech signal and then you store it. The accuracy of this type of representation is specified by two factors. One is the sampling frequency, which is the step in time between n and n+1 samples. That is the n sample and the n+1 sample. The step in time between this, that is the sampling frequency. And secondly, the accuracy and distribution of the amplitudes of xn. Okay. So so what we have exactly, the speech signal, we have the different amplitudes with respect to time. So the speech signal is a one-dimensional function of a one-dimensional variable. Okay, one-dimensional function of air pressure and a one-dimensional function of variable. And what is the variable? It is the time. So this now again, although it's very simple, we have been producing it without even thinking. We don't have to give much thought before we produce any speech signal. But this speech signal is a very complex signal. Why I say complex is because the processing of the speech signal also is very complex. Mainly, I would say the speech signal is complex because it involves a lot of variability. For example, you can see that the speech signal which is produced, the same sentence, suppose, the signal which is produced by a male speaker will be different from that produced by a female speaker. Similarly, the speech signal which is produced by a child will obviously be different from that produced by an elderly person, say, for example. Again, the speech signal will vary based on the mood of the speaker. That means the mood, or maybe the time of the day also, when when the person is affected by the time of the day, or maybe health issues. Health issues also might be affecting. So this way, there's a lot of variability in the speech signal, because of which the processing is also very complex. Now, how a speech signal is stored. For example, you might have come across the speech signal, the resolution of the speech signal is say 16-bit, the sampling frequency is 16 kilohertz. So if I say 16 kilohertz sampling frequency, what I mean is that in 1 second, 16,000 samples have been taken. Okay, so one second, I'm taking 16,000 samples, and each sample is represented by a 16-bit value. Okay, that is the resolution, and I say it's a 16-bit sample. So that is the resolution. So higher the resolution, obviously better will be the representation of the speech signal. However, it will be requiring more and more memory. So if you keep on increasing the sampling frequency and you keep on increasing the bit resolution, there will always be a maximum value, because beyond that there will be no change. So it's not advisable to go beyond that. But you have to select a bit resolution and a sampling frequency in such a manner that if you want to recreate the speech signal from the samples, you should be able to recreate them. Okay, so that is where the Nyquist theorem comes into, which states that the sampling frequency should be greater than or equal to 2 times the maximum frequency which is present in the speech signal. Okay. The most typical format for storing sound signals is the wave file format, which we will be using. I'm using the wave file format. There are other formats also, like one format you know about audio files, the MP3 format or the MP4 format. But for research purposes, for processing, the wave file format is very preferable. Now coming to the speech production process. We have been producing speech, as I said, but we do not fully know exactly how we are producing the speech sounds, right? We might not know. So as you can see in the left-hand side, you can see this is the diagram of the cross-section of a human body. And you can see that this is the lungs, where the air pressure is formed, and it is the lungs inside the chest cavity. So you force out air from the lungs, and this lungs, the air rushes out or goes out through the trachea, and these two small little things that you see, these are 2 flaps of muscles here, which are referred to as the vocal folds. So these 2 flaps of muscles, that is the vocal folds or vocal cords, they can close and they can open, right? So when air forces out, it forces out through these vocal folds, making them vibrate, and then the air moves out through the epiglottis, and then it can either move out through the mouth or you can move out through the nasal cavity. Again, whether it flows out through the nasal cavity or not, that will depend upon the position of this portion, which is referred to as the velum. So if the velum, it acts like a valve. So if it closes this, then obviously the air that you are forcing out will pass out through the mouth. And if this is open, some part of the air will also pass out through the nose, because of which you are producing the nasal sounds. This is a schematic of the speech production process. You can see here, the lungs is represented by a piston here, and you can see that the muscle force, because of the lungs, is pushing the air through the vocal cords, and thereby normally the vocal cords will be closed, and when air pushes out, it will start vibrating, right? It will open and close, and that is the vocal cords are vibrating. And this air will pass through the pharyngeal cavity, and then it will come out through the oral cavity, through the mouth, or through the nasal cavity, through the nose. Now, the speech production mechanism is also represented in this way. That is, this is the source filter theory of speech production, where the vocal cords at which are vibrating, that is the source of speech sound, that is referred to as the source, and the vocal tract, which comprises of this pharyngeal cavity, the nasal cavity, and the oral cavity, that is the vocal tract, that is referred to as the filter, because this vocal tract has the capability of rejecting certain frequencies, that is attenuating certain frequencies, and allowing certain frequencies to pass, just like a filter. Okay, it will allow certain frequencies to pass and it will stop certain frequencies, that is, it will not allow certain frequencies to pass. That is why in the source filter theory of speech production, the source is this vocal cord and the filter means the vocal tract comprising of these different cavities. So now you are familiar with the speech production mechanism. So let us see how the speech is communicated. Okay, so this is a two-way process from the talker to or the speaker to the listener. So how do we communicate with each other? Speech is the most intuitive and the most preferred means of communication between human beings, is it not? So how do we communicate? First of all, the message that I want to convey, that I'm going to form it in my brain. Then I will decide what language to use. Then I will do the message coding. I will be using grammatical rules and I will be using prosodic element. That means what type of tone I want to use, which words I want to stress, and so on. And then I will instruct these signals, that is, I will create nerve impulses, which are the neuromuscular commands. So the brain is going to send some motor commands. And what are these motor commands? To move the articulators. And what are these articulators? The articulators are my lips, my tongue, my teeth, my jaw. These are all different articulators. And I'm going to move these to produce the speech sounds that I want to send. And on the other hand, that is in the listener side, the speech that I'm sending will fall on the ear of the listener. That's why you have the speech perception system, which is going to perceive the sounds that I'm sending. And then this is going to be converted to nerve impulses, which are going to be comprehended in the brain. That means the message that I'm sending will be decoded in the brain. So this is the process of speech communication. This is also referred to as the speech chain. Okay, the speech chain. Now, as I already told you, the speech signal contains a lot of information. So a very generic way of categorizing this information is the information can be explicit information or it can be implicit information. So explicit information refers to the actual message that I want to convey. So when I'm saying that I am giving you a presentation, then you know what I'm saying, isn't it? You understand the message that I'm trying to convey to you. So that is explicit information. Whereas when you listen to my voice, you know that I am a woman. You can, from my voice itself, you can have an idea about my age maybe, right? Or my health condition. So these are all implicit information, okay? So these are implicit information. Now it's whether it is explicit or implicit, the information content of speech can be divided into three broad categories. That is the linguistic information, paralinguistic information, and non-linguistic information. So linguistic information means the content, that is the message that I'm trying to convey. So the meaning of words, then the dividing the words into syllables to phonemes. So all these phonemes and syllables and words, these are used to compose the sentence that I am uttering. So from here you get the basic idea of the message that I am sending. So that is the linguistic information. And paralinguistic information comprises of the prosodic elements, like how I am saying now. When I'm saying something, I'm stressing certain words, right? My tone is changing. So sometimes my tone is increasing, sometimes my tone is decreasing. So all these things are comprise the paralinguistic information. Then non-linguistic information are the speaker properties. For example, the age, gender, individual morphological characteristics, condition of health, etc., which identifies the speaker. These parameters are actually not controlled by the speaker. So these are the non-linguistic information. So now in terms of the information, that is the different types of information, linguistic, paralinguistic, and non-linguistic, I'm defining again, or I am presenting before you the speech production process, where you can see that the message planning is being carried out using linguistic information and rules of grammar. Then once the message has been decided, then the utterance planning, that is the sentences that I'm going to utter, using rules of prosody and the paralinguistic information, I will produce my utterances. Now, after that, the motor command generation, that using physiological constraints and paralinguistic information, non-linguistic information, I'm going to create those stimulus to the brain, which is going to generate the motor commands to move the articulators. And finally, physical constraints are taken into account, and taking into account the non-linguistic information also, the speech sounds are produced, and these speech sounds contain features which are the segmental and suprasegmental features. So here again, I'm introducing you to two new terms, segmental features and suprasegmental features, which I'll show you what they are. So segmental features are characteristics local to a discrete segment of speech. So the basic segment, or I'd say the basic element of the speech, that is the phonemes, which may be vowels, which may be the consonants. So these are the segmentals, segments or segmentals also. And the features or characteristics of these segments, they are the segmental features, right? So we also have subsegmental features, where the particular segment is broken down into multiple subsegments, and then you extract the features of the subsegments. So whatever be the features may be pitch, which is the perceived frequency of a sound. It may be stress, that is the emphasis that we put on a particular syllable in a particular word when we are speaking, or the duration, which means the length or the time taken to produce a syllable, or the time taken to produce a word or a sentence, or maybe the rhythm, that is how fast I'm speaking, the how the tone is varying, that is intonation. So all these are different features, and these features can be segmented also, because if you extract these features from the segments, that is the phonemes, then those are segmental features, and they can be suprasegmental or prosodic features also, where the segment exceeds or moves over multiple segments. That means suprasegmental features, they will extend over multiple syllables. Say for example, multiple syllables or multiple words. That means over a particular phrase, you are extracting the features. Then those are referred to as suprasegmental features. So why we are doing this speech processing now, and what exactly is speech processing? So we know what is the a speech signal. We know how the speech signal is produced. So we have seen the different speech features, and now what exactly is speech processing? The study of speech signals, very simply put, the study of speech signals and the processing methods of these signals, that is referred to as speech processing. So basically what happens, we are converting the signals into digital representation, and then we carry out signal processing on this digital representation. So speech signal is nothing but digital signal processing as applied to the speech signal. So in speech processing, we will be talking about various aspects of speech processing, such as how the speech signal is, the acquisition of acquiring the speech signal, that is the acquisition, manipulation, how you can manipulate the speech signal by manipulating various features, storage, transfer of speech signals over communication channels, and so on. Some of the disciplines which are related to the speech processing mechanism or the task of speech processing are obviously digital signal processing, physics, because we are talking about sound waves, then linguistics, then phonetics, natural language processing, machine learning, artificial intelligence, etc. etc. So the speech task. What are the different speech tasks which are required for man-machine interface? So this is the reason why we are studying speech processing, isn't it? Because nowadays there are a number of tasks which are required for speech tasks which are required for man-machine interface. And these are, some of them I've listed here, as you can see. Speech recognition. What is speech recognition? It is the process where you convert speech to text. So this is one speech task. Again, speech synthesis, which is just the opposite, that is text to speech. Then speaker recognition, that is the input is speech and the output is the identity of the speaker. Language identification, input is the speech signal and the output is the language of the speech signal. Speech enhancement, where the input is noisy speech and the output is clean speech. Speech summarization, this is another task where the input is speech and or a spoken document, and the output is the summary of the spoken document. Then spoken document retrieval, where the input is the speech corpus, and then you have a query, and from there the query is used to retrieve the query document. Then speech coding, where the speech is encoded, then passed through a channel. On the other side, it is decoded, and from the and you get the original speech. Then speech emotion recognition is again a very popular and important task, where you can recognize the emotion of the speaker. So the input is speech sounds and the output is the emotion. And that way we have other tasks also, for example, speaker diarization, where given a particular speech signal which has multiple speakers, you find out which are the different segments which belongs to the different speakers. Now we are moving on to the main signal analysis part. The first type of analysis that I'll be talking about is the pitch analysis. So when I say pitch analysis, the first thing is what exactly is pitch. So you must have heard like someone say, or you yourself, you might have said that so-and-so person has a very high-pitched voice, okay? The pitch of that particular person is very high. So what exactly do you mean by that pitch, right? So pitch is actually how the fundamental frequency is perceived, okay? Pitch is related to the perception, how we perceive in the brain, okay? So how this pitch now or the fundamental frequency originates. In the speech production mechanism, I already told you, when the air is forced out from the lungs, it passes through the vocal cords. And when it is forced out of the vocal cords, what it does, it vibrates the vocal cords, isn't it? Vocal cords or vocal folds. So this vibration, the frequency at which this vocal folds vibrate, that is the fundamental frequency, okay? That is the fundamental frequency, and how you perceive this fundamental frequency, that is referred to as pitch. The acoustic correlate of pitch is the fundamental frequency, whose unit is in hertz. It's a frequency, so the unit is in hertz. So this pitch is an important attribute of voice sound. So here again, you might ask, what is voice sound, right? So when I'm producing the sounds now, when the vocal folds are closed and the air rushes out, it causes vibration, and what you hear is the voice sound. If the vocal folds are open, then what will happen? Open or partially open. Then what will happen? The sound that is produced by the air flowing out of these vocal cords, that will be the unvoiced sounds. Okay, that is unvoiced speech. And if there's nothing coming out of your vocal folds, that is your silence region. So pitch is associated with voice sound. So these voice sounds, usually they are the vowels. The vowels are the voice sounds. Not only the vowels, there are the semi-vowels are also voiced. And then there are other voiced components like the consonants. Some of the consonants, you have voiced consonants as well. Some of the voiced consonants like the b, d, g, like in English you have b, d, g. These are also voiced sounds, okay, voiced sounds. So how this pitch is extracted, I will not be discussing the pitch extraction methods, but the commonly used pitch estimation methods are using autocorrelation function, using the capstrum pitch determination, and another method referred to as the SIFT or single inverse filtering tracking technique. These are various techniques which are used for estimating the pitch of a speech signal. So we'll not be discussing this, but we will see why pitch analysis is important, and we will see how the pitch can be extracted using the PRAAT. So why this type of analysis, that is the pitch analysis, is important? Why do we need pitch analysis, right? Because we know that pitch is an important attribute of voice sounds, so it can also be used, this pitch values can also be used to distinguish between voiced and unvoiced sounds. And pitch contains, this feature contains speaker-specific information. Like I said, for a particular person, the pitch values are very high, right? For a particular person, it can be very low. So using these pitch values, you can also use it for speaker identification. So the speech values, pitch or fundamental frequency values are also used for automatic speech recognition. Then it is also specially important for speech recognition systems for tonal languages. Why tonal languages? Because In tonal languages, you know what's a tonal language? In a tonal language, based on the tone, the meaning of a word changes. That means the same word, if you speak in a particular tone, that means, say, for example, a high tone or a falling tone, a low tone. So if you speak in a different tone, the meaning also is going to change. So in that type of a speech recognition system, then pitch tracking is very important. Then pitch is also important for prosodic variations in text-to-speech systems and spoken language identification as well. It is used for speaker identification, like I mentioned. It is used for emotion recognition, because based on the emotion, whether your emotion, that means whether you're sad, whether you're happy, whether you're angry, the pitch is going to change. The pitch of your voice is going to change. Then it is also used for voice activity detection tasks. Voice activity detection means in a speech signal, you are trying to find out those segments where voice activity is present and those segments where voice activity is absent, for example. Pitch can be used to detect the gender of the speaker, because you know that the pitch values of a female or a child is much higher as compared to that of a male. Then pitch values can also be used to discriminate between normal and pathological voices. So this is an application in the medical healthcare field. So in this one, here now you can see here, I am giving you some snapshots, screenshots actually, some figures here. So this is a screenshot of a zoomed voiced speech segment. Right, this is the periodicity. So although you might see, you know that this the sine wave is a very good example of a periodic wave, isn't it? So you know how the sine wave looks like, and when you say something periodic, that maybe a sine wave or a cosine wave might have come to your mind. So when you look at this type of a signal, you can say that it doesn't look like a periodic signal, right? But then if you see, that's why I have zoomed it here. And if you look closely, you will see that there is periodicity here. For example, from here to here, you can see from here to here, this is how the amplitudes are varying with respect to time. So on the x-axis, you have the time, and on the y-axis, you have the amplitudes of the speech signal. So you can see here, this is how the amplitudes are varying with respect to time. And from this point to this point, it is repeating. You can see, again, this particular segment is repeating from here to here. So from here to here, right? So if you can find out the time, because you have this time axis, right? So from here to here, if you take the time and then you take the inverse of time, you will get the fundamental frequency, right? You will get F naught or the fundamental frequency. So this is the voice segment. And this is how an unvoiced speech segment looks like, where there is no periodicity. Similarly, this is another example. So this is exactly what has been zoomed in here. So you can see this is an unvoiced segment, and this is, if you zoom in, you will see that there is periodicity here, and this is a voiced segment. So this is simply a sample showing you how the fundamental frequency is calculated. So you can see where the waveform is repeating from here to here. Okay, so you take the distance in time and then take the inverse of that, you get the fundamental frequency. So here again, this is a word. What is the word? The word is will, W-I-L-L, will. And when you say will, what are the sounds that you are producing? You are producing W, E, and L, right? So W and L, these are consonants, no doubt, but they are glides. So you can see here, for W also there is periodicity, for L also there is periodicity. And obviously E is a vowel, so there obviously will be periodicity. So all of these will have periodicity. You can find out the fundamental frequency. So this is the speech signal for the word. What is the word? Forget. Forget. So for, this is unvoiced. This you can see here, right? And then that is and r. This is voiced. Again you have g. Then this is forget, a and t. So t is unvoiced, g is unvoiced, and a is voiced again, from where you can extract the fundamental frequency. So we will do this using PRAAT. Okay. So is this clear? The pitch analysis part, is it clear to all of you?
Yes,
Yes,
ma'am.
ma'am.
Yes, it is clear.
Yes, ma'am.
Yes, ma'am.
Okay. Okay, so I will move to the next analysis, that is the intensity analysis. So intensity, from the word itself, the literal meaning of intensity is the how intense a particular sound is, or the you have stressed a particular sound. So the intensity is related to the amplitude of your speech signal. Okay. When sound is produced, it creates waves that propagate through a medium, and the maximum displacement of the wave from its rest position is known as the amplitude, which you have already seen. We have plotted the amplitude versus the time, and intensity is nothing but it is proportional to the amplitude square. So what is the square of the amplitude? Square of the amplitude is nothing but the energy that is contained by the waveform. Okay. The energy which is contained in the waveform, that is given by amplitude square, and intensity is proportional to the amplitude square of the amplitude. So if you have a speech signal with a low amplitude, it means that a low amplitude wave, it carries small amounts of energy. So obviously the intensity values will be smaller. And if you have a signal, suppose, which carries high amount of energy, so in that case, the amplitude, what will be the intensity? The intensity will also be higher. The intensity of a sound is the power of the sound in watts divided by the area the sound covers in square meters. And the loudness of the sound relates the intensity of any given sound to the intensity at the threshold of hearing. That is how we perceive the sound. Okay, so there, how we are hearing it. So that is measured in decibels. The threshold of human hearing has an intensity of about, you can see the values here, 0.000001 watts per meter square, and this value actually corresponds to 0 decibel. So a whisper, when we are whispering something, that what is the intensity of the whisper? It usually falls around 20 to 30 decibels, and noisy conversation is about 50 decibels. A vacuum cleaner, the sound of the vacuum cleaner is about 70 decibels. The sound of the lawn mower is about 90 decibels. A car horn at 1 meter distance is about 110 decibels. So this is how the intensity of different sounds vary. Now, on this figure, this is a screenshot from the PRAAT tool. You can see this is the waveform, that is amplitude versus time. And this part of the window, I'll come to this later. This is called the spectrogram. And on the spectrogram, the blue lines that you see, those are the pitch contours or the pitch values, right? And the yellow line that you see, those are the intensity values, and the entire waveform that you can see, the yellow waveform that you see, that is referred to as the intensity contour. The intensity contour. So how it varies, you see how the intensity is varying here. I do not exactly know what this sentence is, the words and all, I don't know the sentence, but I can say that the intensity is going up, it is rising, it reaches the peak, it falls, again it increases, falls to some extent, again it increases, falls, increases, falls. You can see a pattern, right? And this intensity, again, this particular screenshot that I took, actually, that was for finding out the nuclei of a syllable. You know what's a syllable, right? When I say a particular word, for example, any word, suppose intensity. So when I say intensity, I will say the syllables are in, ten, c, t. So these are different syllables. Okay. So any word, if you say detection, then it is detection. So these are the 3 syllables in the word detection, right? So the intensity contour can help you find out the number of syllables in the sentence. For example, because you see that every syllable will have a nuclei, right? We'll have a nucleus, and you see that the intensity reaches the peak value at the nucleus. Okay. So if you count the peaks here, the number of peaks that you can see here, that will give you an approximate idea of the number of syllables in this particular sentence. That is one application that I'm mentioning here about intensity analysis. So intensity control can be used for accented text to speech. Okay, when you are trying to incorporate a particular accent in a particular TTS system, that is a speech synthesizer. Then detection of stressed speech, because whenever you stress a particular word, when I'm stressing something, what is happening? I'm putting more stress into a particular word, which means the intensity will be increased, right? And emotion recognition also. So the emotion of a person, that also there also, because based on my mood, I'm going to change the intensity at which I am going to speak. So I'm moving on to the spectrographic analysis, which is probably most widely used technique for studying the acoustic phonetic characteristics of different phonemes in a language. So there's a very popular analysis, spectrographic analysis, using what is called a spectrogram. So what exactly is a spectrogram? Does anyone know what is a spectrogram? Yes,
It is a,
Dixon. Yes.
it is a visual representation of a speech where there are frequencies and the loudness is also considered here.
Yes, exactly. Very true. Very true. So you get three information. That is, you have frequencies, and you have time also. Another information is time, and you also know the intensity of every sample. It's a three-dimensional, right? So this is the information that you get from a spectrogram. So it's a visual representation of the spectrum of frequencies of a signal. So when I say spectrum, what is spectrum? Spectrum refers to the frequency content of a speech signal, right? But spectrogram also has frequencies, but how it is different is that in the spectrum, you do not exactly know at what instant of time, what are the frequencies that are existing. And you also, right? Because you'll get the frequency content, you will get all the frequencies which are present in a particular signal, suppose that is the spectrum, but it won't tell you which frequency is present at which instant of time, right? So spectrogram will give you that information. So spectrogram displays the signal strength over time at the various frequencies present in a waveform. I will not discuss how the spectrogram is built, but the final graph or the spectrogram that you get will have time along the horizontal axis. It will have frequency along the vertical axis, and the amplitude that you rightly mentioned, that is the intensity of the sample, that will be present as a colored value, that will be present in the grayscale, right? So more intense the sample is, it is more likely going to be dark. It's going to be black. So conventionally, black is used to signal the most energy, while white is used to signal the least energy. So I didn't talk about formant analysis. After this, I'll be talking about formant analysis. But formants are something which you can visualize in the spectrogram also. And what are these formants? The formants are nothing but the resonance of the vocal tract. Like I already told you, the vocal tract is the filter, isn't it? The vocal tract is the filter, and by making different shape of this vocal tract, that is the filter, then I'm producing different sounds. I'm actually making different shapes of my vocal tract. That is, I'm moving my jaws, so the oral cavity is changing. How my lips are changing, whether I'm making my lips rounder or maybe I'm opening my mouth, then how I am shaping my vocal tract. So everything is responsible for forming the sounds that I'm producing, and the resonances of these, that means the vocal tract, because the vocal tract, as I said, is going to attenuate certain frequencies, and at the same time it is going to augment certain frequencies. Those are the resonant frequencies, okay, and those are referred to as the formants. So these formants, they can be seen very clearly or very well in a spectrogram. They appear as dark bands in the spectrogram. So I'll show you the spectrogram and the formants and all that. The two types of spectrograms are used. One is the wideband spectrogram, WB spectrogram, and the other is the narrowband spectrogram or NB spectrogram. And again, what is the difference between these two? In wideband spectrogram, the sample window or the frame that I'm using, okay, the frame that I'm using to sample So that in WB, that is wideband, it is taken around 5 millisecond frames. So 5 millisecond frames are extracted from the speech signal, and then you compute the FFT and then you plot it in the spectrogram. So that is for wideband. Whereas in narrowband, your window or your frame size is much larger. Say this is the 50 millisecond. You take around 50 millisecond frame size, right? And wideband spectrograms, they are used to measure formants, because when you use this type of a frame size, that is wideband, that is 5 millisecond frames, you get WB spectrograms where you will see the vertical striations. You will see vertical striations on the spectrogram, and you will see the dark bands, that is the formants. Whereas in the other case, that is in narrowband spectrogram, you will see the horizontal striations from which you can extract or find out the fundamental frequency. So here you can see these are examples of spectrogram. So this one is a wideband spectrogram, and you can see that these are the vertical striations. You can see vertical striations here, right? And you can see the dark bands. These dark bands correspond to the different formants. For example, this corresponds to the first formant, this is the second formant, this is the third formant, and so on, right? So looking at this, if I look at this, I automatically know that, okay, so here you are seeing formants, and these are the voice sounds where you can see the formants. Okay, so here again you can see formants. So you can see that, okay, there's a possibility of a vowel existing here. So now in this one again, in this diagram, this is the speech signal. This is the wideband spectrogram which contains the vertical striations, and from here you can see the formants. And this is the narrowband spectrogram where you can see horizontal striations. And from the horizontal striations, you can get the fundamental frequency. Let me show you here. Here you see the horizontal striations are very clear. So these horizontal striations, if you extend it this way, so on this axis, you have the frequency axis, right? 0 kilohertz, 1 kilohertz, 2 kilohertz, 3 kilohertz, right? So if you extend, you come to the vertical axis. This point, whatever is the frequency, that is the fundamental frequency. That is the fundamental frequency. And the remaining striations, for example, this one will correspond to the first harmonic, then second harmonic, third harmonic, fourth harmonic, and so on of the fundamental frequency. So this is F0, which means this horizontal line corresponds to F0. The second horizontal line will correspond to 2 F0. This will correspond to 3 times F0, and so on. Okay, that is what I mean by the harmonics. So spectrographic analysis, they can be used to identify voiced, unvoiced, and plosive. Plosive means the consonants, the plosives, the stop consonants, and then the silence regions also. These can be recognized using a spectrogram. Okay, for example, from these sounds you can know that this is, say for example, this particular segment is a vowel. So I can see that there are silence regions here, right? Same way, I will not go into detail here because it takes a lot of experience to study a spectrogram. So even if you don't know anything, you don't even if you have not listened to the spoken utterance, by looking at its spectrogram, you can at least try to find out, or you can at least predict this spectrogram corresponds to so and so utterance. You can try to formulate the words and try to find out what exactly is this speech signal corresponding to which particular sentence. The last type of analysis that I'm talking about is the formant analysis, and after this we'll move on to the part 2. Okay, so formants, now I've already told you what are the formants. These are the resonant frequencies of the vocal tract, and these are again very important to characterize the speech sounds. Mainly for characterizing vowel sounds, formants are very important. Okay, so the formants are numbered in order of the frequencies. For example, around 5, 6, 7 formants are there, but most of the information is contained in the first, say, 2 or 3 formants. The formants are referred to as first formant F1, second formant F2, third formant F3, and so on. These are again frequencies, so obviously the unit will be hertz. The frequency location of a formant, especially F1 and F2, are closely tied to the shape of the vocal tract as lips, tongue, pharynx, and jaw move to articulate the consonants and the vowels. Vowel formants show up as dark horizontal bands along the spectrogram of the speech sample. The higher the horizontal band on the spectrogram, the higher the frequency of the formant. Now, coming to the formants. The three formants in particular, that is the first, second, and third formant, they help us to distinguish one vowel from the other. Okay, as I said, these vowels are used to characterize the these formants are used to characterize the vowels, so they will help us to distinguish between the different vowels. The position of your mouth when you produce a vowel determines the structure of the vowel sound that you are producing and the structure of the vowel's formant frequency. So these formants, F1, F2, F3, these formants, they will give you information about the vowel's relative height and backness. That is how much your mouth is open, what is the height of the tongue, the position when you are forming these different words, what is the height of the tongue, and the backness, that is where is the position of your tongue. The tongue is positioned towards the front of your mouth or towards the back of your oral cavity. So all this information you get from the formants, and that those information can be used to find out what exactly is the vowel sound that is being produced. For example, the F1 tells you how high the tongue is situated in the mouth. Okay, F1, that is the first formant, tells you how high the tongue is situated in the mouth. Higher the vowel, lower will be the value of the first formant. So this F1 corresponds to vowel height. Then F2 tells you how far back the tongue is situated in the mouth, and this F2 formant corresponds to vowel backness. So the further back the vowel, the lower it will be the F2 values. F3 is not as informative as F1 and F2, but still it helps to signal R-colored vowels. R-colored vowels are those vowels where a small, you can say, the R sound is, the R sound is inherent. For example, when I'm saying bird, I'm saying the vowel but there is some tiny bit of R also, R also in that. Okay, so those are the R-colored vowels. So F3 will give you information about the R-colored vowels. So R-colored vowels have a very low F3 value compared to other values. The F3 values will be very low for R-colored vowels. Now this is this diagram that you can see. Can you see the this diagram on the right? This one that you see, these are all possible vowel sounds. These do not pertain to a particular language. So these are different vowel sounds. Some of the vowel sounds you are familiar. For example, this is E, A, A, O, U. These are all different vowel sounds. Okay. So here in this one, this is the IPA chart actually. So what is I assume you are familiar with the IPA, that is the International Phonetic Alphabet, which contains all possible sounds in all languages. So there's a unique symbol for all the possible sounds that can be produced, and that the set of all those symbols, that is what is the IPA chart. So these are all different vowel sounds. As I said, that all these sounds do not belong to a particular language. So for example, English may have some of this, Hindi may have some of these vowels, right? And you see this is referred to as the vowel chart also. So from here to here, this x-axis will have F2, that is the second formant F2, and the F2 increases from here as you move from right towards the left, the F2 increases. So higher the value of F2, more front will be the vowel that is being produced. And on the y-axis, F1 increases from top to bottom, right? So when you F1 increases from top to bottom, so you can see here, this is the closed vowel, where this is the open vowel. So when I say oo, my lips are rounded, so it's a closed vowel, and when I say ah, then my mouth is open, so this is a open vowel, right? So these are different information that you get from this vowels, vowel chart, and this vowel chart is how the vowels are placed in this chart. That is by using the first two formants, that is F1 and F2. So using F2 and F1, F2 on the x-axis, F1 on the y-axis, we have formulated or designed this vowel chart. And now by looking at this, the different sounds here, you can say the characteristics of that particular sound. Like I said, for oo, The oo sound or oo vowel is produced at the back of my mouth and it is a closed vowel. So here's a link. You can, if you go to this link, you will come across the IPA chart where you can click on the different vowel sounds or the consonant sounds if you want to listen to them. Now, there are different techniques which are used for extracting vowel formants like linear predictive coding, Fourier transform, capsular analysis. We are not going to talk about all this, but what we will see using the PRAAT tool, we'll see how the formants can be extracted and how we can construct the vowel chart. Okay, so you can see here in this diagram, you can see the different vowels, that is R, E, A, O, U. These are different vowel segments. This is the one segment corresponding to the sound R. This is the segment corresponding to E. This is A, this is O, this is U. And you can see the dark bands of energy that you see. These correspond to the F1, F2, F3, F4 formants. So from this, you can find out the values of the formant frequencies, and you will see that for all these different vowels, the formants are different. So by looking at the formant values also, so by looking at this formants, you can say that okay, if the formant is this, that is F1 is in this range and F2 is in this range, then this particular segment obviously belongs to so and so vowel. This is a spectral slice again, which you can take from using the PRAAT tool. And if you look at the spectral slice, this is which is a slice of the spectrum. The peaks that you see here, this is one peak here, this is another peak here, this is another peak here. So these peaks are actually the formants. This is the first formant, this is the second formant, this is the third formant. So what PRAAT does is that internally PRAAT has an algorithm which will be, it will be using a peaking algorithm. I think it's using the Berg's algorithm to find out the peaks, and those peaks correspond to the different formants. This is how PRAAT is going to find out the formants in a particular speech segment. So this is just a sample. So some studies we have been carrying out in our lab where we are studying the vowel formants, the formants for vowels corresponding to different languages. These are the vowels that have been extracted for a particular language, and you can see using PRAAT, the vowels have been, the formants have been extracted like F1, F2, F3. These are the vowels corresponding to the, these are the formants corresponding to the vowel R. Then similarly, these are the formants corresponding to the vowel A. So all these you can extract. This data, it has been extracted using the PRAAT tool. And then finally, what you do, you find out the average values of F1, F2, F3. So in this Excel sheet, you see the average values of the different vowel sounds. And then you can plot it. You can plot it by taking F2 on the x-axis and F1 on the y-axis. Okay, and then what you get is something which is referred to as the vowel chart. So this vowel chart is very important for language identification also, because using the vowel chart you will be able to distinguish, because it is not that the vowel sounds that are in English should be in all those vowel sounds should be in the Hindi language, or the vowel sounds in the Assamese language, suppose. Those vowel sounds, all of those vowel sounds may not exist in the Hindi language, isn't it? So that is how that is the information that you get from the vowel chart of a particular language. As you can see, this is the vowel chart for the English language, where you can see this is E. Okay, so here the points. This is E as in hit, and this is E as in heat. Right? So this is hoot and this is hoot. Right? So you have two different types of oo, and you can see these 2 points corresponding to the different sounds, the oo in hoot and the oo in hoot. Right? Similarly, this is pot, the o in pot, and this is the o in pot. Right? So this way, this is the a in bat, and this is the a in bet. Right? So you can see that the sounds are different, and the 2 points correspond to those different vowel sounds. So basically you get something like this, and you can see here, this is F1. From top to bottom it is increasing, and F2 you can see it is increasing from right to left. So in a similar pattern, we have plotted the vowels of the Assamese language also, and we get something like this. So you can see that if you can compare the vowel charts to find out how two languages may be different in terms of the vowel sounds. So now we move on to PRAAT. It's already 1 o'clock. We'll just have, we'll see. So all of you have PRAAT downloaded, I suppose. So you can open that PRAAT tool, you can open it. So basically PRAAT is an open software tool which is used for the analysis of speech in phonetics. And it has been designed and it is still being developed by Paul Boersma and David Winning of the University of Amsterdam. It is free and available for most platforms. So I think you have downloaded it, whether it is for the Linux platform or for the Windows, that particular version is available. Then target readers of these are those beginners who are not equipped with a strong phonetics or programming background, but still you want to do some phonetic analysis of speech sounds. Then the PRAAT tool will give you a clear visual representation of operational procedures and introduction to acoustic knowledge. So these are provided to facilitate the use of PRAAT in linguistic research. So these are the things that can be done using PRAAT. This is not all, but there are others as well. So some of the most commonly type of analysis or the tasks that you can do using PRAAT, you can see it can be used to generate waveforms, like you can generate spectrograms also, wideband and narrowband. You can generate intensity contours, speech contours. Then you can make recordings. You can record your voice. Okay, you can save the recorded voice. Then you can do some sort of preliminary processing. For example, if you want to remove noise, you can remove the noise. Then you can try to extract features, whether it is speech features, intensity, formants, etc. You can extract those features. And then you can extract the features and then store them into Excel files as well, which can be used for further processing. Now, at the same time, there's another task which is very important when developing corpus. For corpus building, you need to annotate the speech sound. That means you need to label the waveform. Whatever speech waveform you get, for example, for a particular sentence, you might have to break it up into words. That means you might have to label the words, or you might have to label the sentence. And within a word, you might have to label the syllables. So then you might have to label the part of speech, that is part of speech tagging. We say it's part of speech tagging, right? So a particular segment, a particular word, what is the part of speech, right? So those type of labeling can be carried out using PRAAT textbooks. Okay, so we'll see that. And then PRAAT can be used for giving you different figures and also for visual representation. And then PRAAT scripts, though we'll not be talking about PRAAT scripts, but some of the things need not be done manually. You can write some scripts also to carry out those tasks. So that those are called the PRAAT scripts, and you can use those PRAAT scripts also to do, if you have multiple operations which needs to be done repeatedly, you can write a PRAAT script to do that. So these are some of the links. The first link is for downloading PRAAT tool, and these are some links for some manuals. So you can download these manuals. If you want to work with PRAAT, you can download these manuals. So at this point, may I know how many of you have used PRAAT? How many of you are familiar with the PRAAT tool?
I think nobody.
Oh,
No.
is it?
Dipsankar, you know PRAAT?
No, sir.
No.
Okay.
Okay, that's very good then. At least I'll be telling something new then. So it's good to know that. So this is the PRAAT tool. Oh, is it visible to you? Can you see the PRAAT tool now? No.
No, ma'am. No, ma'am. You have to share the multiple screen, then only.
Yeah, I'll just do it. Wait.
That's in the output.
Can you please share your
All of you just install the PRAAT if you have, so don't have. I've already sent the link yesterday.
can we have access to these slides? Or
Yes, yes. Everything will be uploaded in YouTube. Don't worry. And a link will be given to you. It's visible now, ma'am.
Yes, it's visible right now.
Yes, ma'am, but no voice is coming, but visible. Your voice is coming.
My voice is coming. Okay, I haven't seen anything. Okay. So I will play a audio, and please let me know if that audio is audible to you or not. So
Ma'am, have you clicked on the share audio or share video there? That option.
no.
Otherwise, reshare that one. Right hand side one share video option.
Okay. I have just played an audio. Can you hear it?
No, ma'am. You
No,
have
right?
yeah, stop sharing and you have to reshare that audio option. The
Okay.
right hand side. Whenever sharing, in the right hand side, one share audio option will be there. Share
Yes.
video option. Yeah. That you click then only. Along with the multiple screen.
Okay,
Yes.
I'm playing it.
Della finished her cry and attended
Yes,
to
coming.
her with
It's
the
coming,
powder
right?
flag.
Okay, fine. Okay, so this is the PRAAT main objects window. Okay, so suppose I've already opened the file here. Let me just show you. First, I'll just show you how to record a sound. Okay, suppose I want to record a sound. So this is how I'm going to record my sound. So here you can select the frequency, whatever sampling frequency you want. Say, for example, I'm selecting 16 kilohertz sampling frequency and mono channels. So when I want to record my voice,
that window is not visible where you are selecting the frequencies and.
okay, just a minute. Okay, just a minute. So I have to share each and every window, right? Now, can you see it?
Yes, ma'am. Yes.
Okay. So when I am recording this, when I press this, that is new record, right? Record mono sound. This is the window that came. And if I want to record now, what I'll do is I'll press the record button, right? So let me just try. Can you hear me? So stop. Okay. So once I stop this now, what I can do is I can save it to a particular file. Say, okay, I can save it. This is the name that I have given, so I can save it somewhere. Save as a WAV file. Suppose AAA. I'm saving it. Okay, so I have saved that WAV file, and now I can open that saved file. Whatever file I saved, see, I have opened it now. That means the sound that I recorded, I no longer need this. This is what. So, can you still hear me?
Yes, ma'am.
But screen is not visible.
Yeah. Which is not visible now? The PRAAT object window, is it visible?
Ma'am, nothing is visible.
ma'am.
No.
Just a minute.
It's visible now, ma'am.
Yeah, just a minute. Okay, so I'm playing this now. So the waveform, can you look at the waveform that I just recorded now?
Yes, ma'am.
Yes, right. This is the file that I just recorded. So I'll play it. Can you hear me? So this is the main portion where this is the sentence. Can you hear me? Can you hear me? Right. And you can see that this is a very noisy signal, right? These are all noise. This is because of the fan that is running in my room. So there are a lot of noise in this, which definitely I would like to remove, right? So there's now filtering. I would like to filter out this noise. And there are different ways of filtering, and there's a filter button here in the object window you can see here. So there's a tutorial which you can go through and see how you can carry out different filtering. So maybe using pass band filters, stop band filters, or maybe you can give a filter formula of your own. And the simplest is simply by pressing the reduce noise button, where you need to select a particular, or you have to give PRAAT a sample of the noise. And then PRAAT will try to eliminate that sample, whatever sample you have given, it will try to eliminate that from the sound. Okay, so in this particular wave file, as I can see that from here to here, this is basically nothing but noise, right? Again, from here to here, this is also noise. So what I can do is usually to give this, I can copy here. Copy, and then I can paste it here also. So now if you see, I have around two seconds here. This is nothing but noise. This entire portion that you see, this is nothing but noise. This is nothing but noise, and this noise is also superimposed on the main speech signal that I want to process. So what I'll do is I'll give PRAAT this sample, and then PRAAT will try to remove this from the entire speech file, okay, from the wave file. So if I press this filter and reduce noise, now see, noise time range from 0 to, as I said, around 2, right? So I can put 2 here. Can you see this? I have to share, I think.
Oh, we can see this.
You can see this, okay. Okay, so see, I have given the time range from 0 to 2 seconds, right? Now, if I apply, there's, see, the noise reduction method, it's using internally, it is using an algorithm, spectral subtraction method, which is used to reduce the noise. So it's going to subtract this particular sample that I'm giving from all the samples. So if I apply this now, I will get the denoise signal, which I'll show you now. I'll get the denoise signal here. This is the denoise signal. See, this is the denoise signal. So you can see that if the noise has been removed, and this exactly is the recorded speech wave file. Can you hear me? Can you hear me? Okay. So now the sound is much clearer with the noise that has been removed. So this is a very preliminary way of removing the noise. Obviously, if the noise is more complex, then obviously you'll have to use other methods. And those who are working in the area of speech processing, you might be familiar with other tools as well. For example, you have Wave Surfer, you have Audacity. These are different tools which can be used for noise removal. Okay. But in PRAAT also you can carry out, this is a very simple example to eliminate the noise in a particular wave file. Now, once this is done, let me, you can save this. If you want to save this, save selected sound as a wave file. So only this I can save. Suppose I'm saving it as a AAA_D noise. So I can save it as this, and then I can open that sound. I can open that sound from, again, wave file. This is the file now. See, I can open it. Now this is my, can you hear me? Can you hear me? Okay. Now, that is one thing that has been covered. Okay. Now coming to the, let me take a particular sentence. I have a sentence here.
Della finished her cry and attended to her cheeks with the powder rag.
You can see the waveform and the spectrogram.
Oh, ma'am, we are seeing the previous spectrogram.
Okay, so which means I have to share. Now you can see it, right?
Yes, ma'am.
Okay, so this is the sentence.
Della finished her cry and attended to her cheeks with the powder rag.
So what the sentence is, Della finished her cry and attended to her cheeks with a powder rag. Okay, so let's not take such a long sentence. I can take a smaller sentence here.
Della finished her cry.
Della finished her cry. So let me select this, and then file, save selected sound as wave file. So I can say sentence. Let me save it as sent1 test. Saving this, close this, and I'm going to open that file.
Della finished her cry.
So now in this one, you can see already the spectrogram is there. So I can intensity, show intensity. So I have nothing to show now. This is mainly the waveform. Okay, this is the waveform. So you can see in PRAAT, if I say show spectrogram, you can see the spectrogram. This is the spectrogram. So in this spectrogram now, like I told you, the two types of spectrogram that I mentioned. One is the wideband spectrogram and the other is the narrowband spectrogram, right? And that spectrogram is, the difference is mainly the frame size. So one uses a around a smaller frame that is around 5 milliseconds, and the other uses a bigger frame around 50 milliseconds. So that I can set then if I go to the spectrogram settings. So if I go to spectrograms here, you can see the window length. This is 0.005, which means this is how much? 1, 2, and this is 50 millisecond, right? So this is 50 millisecond. Okay. So what you are getting in 50 millisecond? What was the waveform? It is the narrowband waveform, right?
Yes, ma'am. Narrowband.
Narrowband. So if I want the wideband waveform, so narrowband waveform, and if I want the wideband waveform, what I'll do is I'll simply change this to say 5 milliseconds. So now it is 5 milliseconds, and you can see, oh, what is it? So here again, you can see there are advanced spectrogram settings also, where the methods which are used are mentioned here. You can change those methods as well. So now I think you are getting better resolution, right? Now you are getting better resolution. This is one spectrogram, and this will give you the other one. Yeah. So here you can see the vertical striations, and here you can see the horizontal striations, right? You can see the horizontal striations here, and in the other one you can see the vertical striations. Okay. Now, if I want to see the pitch now, see, these are the pitch. That means these are the, what are this? These are the fundamental F0 values. So all the F0 values have been connected, and these are the pitch filter. And I can have the intensity. You can see how the intensity is increasing and decreasing. I can see the formants. The red lines, they indicate the formants. So in this formants, maybe I can also set the number of formants that I want. Suppose I want only 4 formants to be shown. I can see only 4 formants. You can increase the number of formants, right? Now in this, let me choose.
Della.
Okay, so this is the word where, okay, this is the word Della.
Della.
Right? So you can see the periodicity here. You can see the periodicity. See, this is dark bin. So obviously this is something corresponding to A. Can you hear this?
Yes, ma'am.
Yes, ma'am.
Yeah. And you can see it, right? So this one, if you see, this is corresponding to the vowel A. right? Now, if I zoom it, I can zoom this further, and then I can calculate the fundamental frequency. So you see what is the periodicity here. So as I said, you're not going to get exactly what you are expecting in speech. That is the ideal waveform that you are expecting. You're not going to get something like that. So in this, there is periodicity, but the periodicity, obviously, it's not like a sine wave, but you can see that from here to here, you can say there's repetition, isn't it? This segment is being repeated, you can see, right? So that is now how good the waveform comes, that also depends on the type of recording, how good is the recording. So from here now, if you select this now, what appears here is the time. Okay, this is the time, right? Can you take the inverse of this? If you take the inverse of this, then what you get is, what will you get here if you take the inverse of this? Frequency. Yes, you will get the frequency, that is the fundamental frequency. So what is the value here now?
240
Your time is this, isn't it? So if you take the reciprocal of this, what do you get? You get around 242, right? So the fundamental frequency is 242. It's 242, right? Now, again, that is how manually I have calculated. Now again, if you select this particular segment, you can also get pitch from here. Pitch, no, not pitch settings, pitch listing. So you have pitch listing, and you can see how the pitch is listed. So you see at this instance of time, 0.51, it is 238, 0.52, it is 240, 0.53, it is 241. You can see
that window is not visible now.
Yes, I'll show you. Yeah. So you see this PRAAT info that you're getting? PRAAT is giving me this information. When I clicked on pitch listing, this is what I got. So you can see that at different time steps, 0.51, 0.52, 0.53, 0.54, these are the values of fundamental frequency, right? So what we calculated was around 242, right? So our calculation was correct because it is something, it is falling within this range, right? So now from here, you can copy and then paste it into an Excel sheet, right? And okay, so that way, now the features, all the features, whether it is pitch or intensity, you can extract. So for example, I can have intensity listing. It will tell me all the intensity values of all the samples in this particular segment. Then I can also get the maximum intensity. For example, if I click on get maximum intensity, it is going to give me the maximum intensity, right? What is that maximum? This one, PRAAT info that I'm sharing. So it is going to show me the maximum intensity. So which means that in this segment, what is the maximum intensity? 75 dB is the maximum value of intensity, right? So that way, now you can extract these values, whether it is formants, you can extract first formant, bandwidth of the formant, second formant, and so on. Okay, so once you select a particular segment, you can extract either the pitch, intensity, formants, etc. Similarly, for the entire sentence also, if you select the entire sentence, you can extract these values and then you can copy and paste it into your Excel sheet. However, when you copy and paste, obviously this becomes very tedious, isn't it? You have to copy paste. Instead of that, you can write PRAAT scripts. So I don't have a PRAAT script with me right now. I won't be able to show you, but you can write a new PRAAT script. You can write your own PRAAT script and then run it, so that what will happen, you can extract you can set the frame rate, you can set the size of the window, you can set the sampling rate, and then you can decide on what are the values, what are the features that you want to extract, whether you want to extract pitch, intensity, or formants, where you want to write those. You can give the file name of your Excel sheet, and then you can run your program and everything will be done automatically. You don't have to do this manual stuff. Okay, so PRAAT scripting, there are tutorials where you can get hold of a PRAAT tutorial, which will tell you how the PRAAT scripts are written, and using those PRAAT scripts, you can extract and save your features. Okay. Now, coming to the formants now, like, yes.
Ma'am, can you show that? Yeah, again, and that del that spectrogram, that spectrogram.
Spectrogram of what?
And the previous one where we have analyzed the fundamental frequencies.
Okay, just a minute. Can you see this?
Yes,
Della
ma'am.
her
Okay.
So
Della
here, ma'am, the red lines are the formats.
Yes, the formants.
Okay, and the green line is the intensity and
Blue line is pitch.
pitch. So,
Pitch.
ma'am, the pitch is the average of all.
No.
All for
These are points. All the points are connected. At every instant, you can like when you do pitch listing, you saw now for every timestamp there is a pitch value.
yes.
Okay, so at every instant of time, the pitch values are extracted and then plotted, and then this is the line joining all those points. That is the contour. This is referred to as the pitch contour. So when we say, for example, here you can see, we say that the intonation. What is intonation? The variation in pitch. My pitch is changing from high to low, low to high, and so on. So this rise and fall, that is referred to as the intonation pattern. So you can see that the pitch is decreasing, then increasing, then increasing. So this is the highest pitch of my voice or that particular voice, of this particular voice. Again, here you can see that pitch is again decreasing in this way. And you will see that the pitch values you will get only for voiced speech, as I said. So for unvoiced speech, you cannot calculate the fundamental frequency. So you will not get pitch values for unvoiced sounds.
Okay. The pitch is actually the fundamental frequency for voice sounds.
Yeah. A fundamental frequency. As I said, pitch is the measurable value is the fundamental frequency. Pitch is something that you are perceiving. Okay, and how do you represent the pitch? You are representing pitch as fundamental frequency values. So just now I showed you how to calculate the fundamental frequency, right? So that is how all those values have been calculated and plotted, and what you get is the pitch contour.
So the F1 and F2 are the resonance. I mean, the pitch, the sound is created in my vocal cord. Then it hits some areas in my mouth and it will resonate and increase the frequency. That is F1, F2, F3.
So, like I told you, the pitch values that you are saying that corresponds, those are source features. Remember in the speech production mechanism, I talked about the source filter theory of speech production. The source is the vocal fold, isn't it? So,
yes, ma'am.
And the pitch is being generated because of the vocal folds. The folds are vibrating and you are getting the fundamental frequency, right? So this pitch are source features, but the formants are filter features.
So for formants, I can able to distinguish the separate vowels.
Yes, formants you can use because every vowel, now again see, if you look at the, you can type in Google, you can find out like the formants for different vowels. Okay, then you will be given a set of vowel ranges. Key for this particular, suppose the formant, first formant is this, F2 is this, F3 is this. But it is not like those are just specific values. It's going to vary from person to person. Your formants might not be the same as my formants, because again, male vocal tract and female vocal tract is not same, isn't it? Males will have a larger vocal tract. Females will have a smaller vocal tract. So obviously your formants and my male formants and female formants, that the formants generated by male and female, they are also not going to be similar. They are going to differ. Likewise, when you say the pitch or the fundamental frequency which is being generated because of the vibration of the vocal fold, the vocal fold are nothing but small muscle flaps, isn't it? So the mass of that vocal folds again will differ from male to female. Male persons will have more mass. The vocal fold will be more massive than the female vocal folds. So obviously the pitch values, that is why we know, you already know, isn't it? Because see, if your vocal fold has more mass, in a male it has more mass, I'm saying. So it will not be able to vibrate very fast, isn't it? That is why your fundamental frequency values for male, they are smaller as compared to females, because for females the vocal folds are not that massy, isn't it? So they will be vibrating more faster. So they will be vibrating higher fundamental frequencies.
So for distinguishing or speaker identification, we will focus on the formats because it is
Yes.
different
Yes.
for every person.
Yes, yes. So whenever we are using formants for suppose, like I said, for language identification and for distinguishing vowels and all that. Suppose you have collected data from lots of speakers. Some of the speakers may be of different. Obviously, they will have different lengths of vocal tract. The size of the vocal tract will be different. Then again, you might have collected data from male and female. So in that case, what we do is we go for formant normalization before you are going to use the formants. You have to normalize. Speaker normalization has to be done on the formants. There are different techniques. Like there is a measure called the Lobanov measure, which is used for speaker normalization. You can use it on the formants.
Yes, ma'am. Another question. You have used spectrograph of narrowband and wideband. So there is another spectrogram I've heard, that male septum spectrogram, log male septum spectrogram. What is that?
That is totally different, you know. There you might have come across features like MFCCs.
Yes.
Yes.
MFCC.
MFCCs, those are features from that male spectrogram. Mel actually comes from the word melody, and it is actually what we perceive. Like it will not be easy for me to discuss the Mel spectrogram. That is again a complex. There are a number of steps by which you can plot that kind of a spectrogram. So this spectrogram, like I told you, how you can do it. You take a segment, you take the Fourier transform, you take the spectrum, right? And then you have to change the axis, you have to plot it. So this is the commonly used spectrogram. Mel spectrogram is something where when that mel comes in, the mel frequency, we say, mel capstrum, mel frequency. So that corresponds to more, that is closer to how humans perceive the frequencies. Because if you see the frequency, suppose a frequency, there might be a frequency difference of say 100 hertz and 200, they differ in 100 hertz, isn't it? So numerically, you know that these two values, they differ in 100 hertz. Okay, but how humans perceive them, that might not be the same. The difference in frequencies, how humans will perceive the frequencies, that is not same. So there is a scale which is called the Mel scale. There's a formula. If you search for Mel scale, you will see how a particular frequency can be converted into Mel frequency. A normal frequency that you know, it can be converted into Mel frequency. Okay. So I think it's past the time. Any other questions? I thought of discussing formant analysis and all that, but there's a limitation to time also. So I'm there. If you have any queries, you can always communicate. You can ask me for more information. Yes, Dr. Ash, I think that will be all from my side.
Yes, ma'am. Thank you very much. Very informative, and so many students or participants are interested. If anyone will try to contact you or can start some new work also, because as you know, here around 110 foreign participants are there, most of them from Africa, from Nigeria, Mali, Malaysia, from France also students are here. So if they want to participate and we can start some new work on speech processing, we can contact that. Definitely, I will contact you.
Speech is something like if you go for a research on speech, it is not like you need to know the language. So without even knowing the language, speech processing can be done. because speech is all about sounds that we hear. So that can be done. Whatever language, we can always work on that speech signal.
Ma'am, can you go for speech to speech conversion, like some African to Chinese?
Currently, one of my research scholar is working on speech to speech translation. So for that, he has selected a particular endangered language of the Northeast, which is the Tiwa language. So from that language, he's going to convert to Assamese and then to English and vice versa. So that he's working on speech to speech translation.
I think we can try for the other languages also, same thing.
Yes, obviously.
Okay, ma'am, then thank you very much. Okay, and another session is there, I think, in the last day, before the last day, I will inform you.
Yeah.
So, okay, thank you
Thank
very
you
much.
so much, and thanks to all the participants for bearing with me.
Thank you, ma'am.
Thank you, ma'am. Namaste.
Thank you, ma'am.
Thank you, ma'am.
Welcome.
So next session will be at 3 o'clock. Okay, Dr. Govind will take. Till now, thank you.
Yes, sir.
Yes, sir. Thank you, sir.